is part of the point of this talk, quantum non-locality. You see, there are these very strange things. Well, it's basically Einstein who started worrying about these things first. He was, I think, trying to poke a hole in quantum mechanics, because even though he was one of the people who started the subject, he didn't like the way it went. Because that's not the only case where that's happened in science. But in this case, he thought there must be something wrong, and so he pointed out things that were very strange implications of quantum mechanics, thinking that they were going to show quantum mechanics was wrong. Unfortunately, in this case, it showed that he was wrong and that quantum mechanics was right. But they were very insightful things to point out, and these contributions from Einstein and his colleagues, Podolsky and Rosen and David Bohm, which is more like the specific case I'm showing you here, he's pointing out that quantum mechanics does have these very, very strange implications. Now here we have something starts off in a state of spin 0. That means there's no direction it's got to it at all. It's a symmetrical thing. And it splits into two particles, each of spin half, so they're like the ones described here. And the spin over here and here have this property that they're opposite. Now I should say, this is one of the very strange things about quantum mechanics. It may be that the thing is spinning in some direction. Now, how would you ever know? Well, you could say, well, let's measure its spin. But the thing is, when you measure the spin, there's only one bit of information you can ever get out of the spin of a spin-half particle. So you choose your direction, say, well, let's try this one. Well, if you tried that one, and you got it right, you see, if you tried that one, you tried that direction, you say, it says, yes, I am indeed spinning that way. If you tried something else, it would only give you a probability. If I tried the opposite one, said, no, I'm spinning the opposite way. If I tried this direction, it would be 50% chance that one way or the other way. That's all you can get. It'll just say yes or no, this way or that way. It won't say no, which direction it's spinning. So that's one of these funny things. The state tells you which way it's spinning, but you don't know what the state is. And you can't tell by doing a measurement to work out what that state is. So it's quite subtle to know that these things are spinning oppositely. You might choose to measure its spin this way, and then you know if somebody else measured this one, it would come out this way, but they might measure it some other direction, you see. Well, John Bell introduced these things called Bell inequalities. I don't think he called them that. That's what other people call them. These are to do with ways of distinguishing this very strange behavior of quantum mechanics from the way in which a classical system could behave. You could imagine that these particles coming out here are some piece of machinery, say, each one. And they start off together with some rules about how the machinery on this one is related to the machinery on that one. And what Bell shows is that the way quantum mechanics behave simply can't be explained that way. If these things are not in communication after they've separated, there is no way that they can imitate what quantum mechanics actually says they do. And this is quantum non-locality. It was really John Bell who showed that these were real things. Quantum mechanics behaves in a way, and it is a very subtle thing, because you might say either these things are in communication or they're not. If they're in communication, this one could send a signal to the other one and say, look, I've just had my spin measured this way. Be careful to measure yours, the other way, something like that. See? You could have messages like that. That's communication. But it's not like that. Because if it was like that, you could violate relativity. You could send a signal faster than light, and that would violate relativity. Because these things could be photons and not spin half. In fact, they usually are photons. In which case, you can't get a signal back to the other one. He couldn't say, look, I've been measured this way. You better make sure you do it the other way. It's too late, you see, because the signal can't get over there. But nevertheless, they are what's called entangled. That word entangled was introduced by Schrödinger to explain the kind of system the situation that comes here. Now, there are examples using photons. I'm not quite sure what the record is at the moment, but the distances, you see, you think of quantum mechanics as being about small things. Okay, the things are small, all right. These could be photons, small in a sense, but they can be awfully far apart. In fact, as far as we know, there's no limit to the distance apart that they can be. And there are experiments which have been performed in Switzerland. I'm not quite sure what the the record is here, but at least over 100 kilometers. So photons separated by 100 kilometers, and they have these entanglements between each other, at which they seem to be part of one system. They can't communicate this information to each other, but you can't explain them as being separated from each other. They're still entangled. Well, the nicest example, the simplest example of this, I'll show you that one, is one by Lucian Hardy of Perimeter Institute, I'm glad to say. So let me try and describe Lucian's very beautiful example. It's not quite what we have here. It doesn't start from a spin 0 system. It has to start from a thing which has spin 1. It's the next case up from spin half. And it's this particular state. You can put it in this state. I've put some arrows here to try and indicate which state it is if you happen to know about these things. But don't worry about it. There's some state here, and it goes off a long way away. These could be, miles apart. And you might choose to measure the spin of these things. Now, the rules of this game are going to be that the person over here, the right-hand person, is going to measure either up-down, and it's going to say, if you say up-down, it's going to say, yes, I'm up, or yes, I'm down, or no to up, if you like, or right-left. There's a choice between those two, up-down or right-left. And the one on the left is going to do the same thing, up-down or right-left. Now, let's imagine that these clever particles here have sorted out between themselves what they're going to do. And then now they're out of communication. So that's the kind of thing that you would think would happen if these were classical objects, certainly. Now, there are certain rules that you find, and Lucian has worked these out, so the rules will always hold. There are 4 things that these people could do. They could measure up, down, left, right here, and up, down there, or left, right, whichever it was. And the rules are that sometimes, this is the only thing which isn't just yes or no, sometimes it must be the case, and it's about probability of a 12th, maybe out of 12 occasions where these things get emitted, roughly speaking, there will be one of these which does the following. That if it happens to be the case that the 2 observers measure up, down, that they sometimes both get down. And that has to happen about 1 out of 12 of the times that they choose it down. So these little particle people down here have to decide that these things must occasionally, 1 out of 12 about, say that if they're measured up and down, they will sometimes give down, down. OK. But they don't know which way they're going to be measured. So it might be that the one on the left didn't do up and down, but did right, left instead. Now, the rules come out. Quantum mechanics tells you that you never get left for this one and down for this one. You never get down for this one and left for this one. And you never get right for this one and right for this one. So those are the rules. OK. Now, what's wrong with all that? Well, OK, sometimes I say it will do this. So let's suppose that these things have come apart, and the one on the left has decided, instead of measuring up and down, left, right. Well, we know that the rules tell us that if this one is going to come down, this one has not allowed to be left, so it's got to be right. OK, but they didn't know it was going to do that, and they might not have done that. They might have done it the other way. This one did do up, down, but the one on the right-hand side decided to do left, right instead. Now, these rules tell you that if this one's going to be down, as it has to be from this one has not allowed to be left, and so it's got to be right. But then, suppose neither of these had been up and down, and this fellow, the people in here didn't know that. So it could have been both left, right. And since this, we found out that this one's got to measure left, and this one's got to measure left, in this case, but that's not allowed. So they can't get it right. You always can catch them out, one way or another, if they are what's called local realistic model. If it's a local realistic model, that is to say that these pieces of machinery which are trying to imitate quantum mechanics, OK, they can confer with themselves right at the beginning and decide what they're going to do, but from there on, they're out of communication. There's no way of imitating this behavior. So that's a nice example nice enough that I can actually sort of explain it here. Can't explain why it does it, but that's what the rules of quantum mechanics come out with this answer. And indeed, this is the answer that experiments give you. Okay, that's space-time seems to have this very strange kind of entanglement built into it. And it's something people genuinely worry about for good reason. Now, I want to try, in order to get to the point where I can explain where twistor theory has anything to say about it,